I'm going to start by talking about a problem that we want to optimize, we want to solve, where there is a solution, but it can't be attained using the methodology we described yesterday. And we'll use this problem to guide us to an alternative methodology. And then I'm going to switch problems on you, because it's somehow, once we've come up with the methodology, it's going to be easier to actually carry it out on a different problem. So the problem I'm going to start with to motivate this new methodology is called multi-terminal cut. Now, this is a favorite problem of mine. You have a graph. With edge weights. And you also have a set of terminals. The goal is to remove a minimum weight set of edges to disconnect all the terminals. There is no terminal-to-terminal path. Questions on the problem? Do you know any method of solving this in the case where the number of terminals is 2? Max flow. Max flow gives you a min cut. What about when the number of terminals is 1? It's just a joke. It's an empty set. Okay. What about when the number of terminals is 3? At this point, the problem is already NP hard. Okay, with just separating 3 terminals from each other. Turns out, though, there is an approximation scheme for planar graphs. So what I want to do is take several steps towards that approximation scheme to motivate this new methodology. So let's say you had a graph. Say it's a planar graph. I don't know what the weights are. We'll assume that there are some weights here. And we have some terminals. Let's add some more nodes in here. Okay, so this is an example instance. Let's see how we would apply the methodology of yesterday's approximation schemes to get an approximation scheme here. So let's recall the basic idea. We want, for some parameter k, depending on the error we desire, epsilon, we decompose this graph in k different ways. Decompose it into pieces. We solve the problem induced on each of the pieces optimally, and then combine the solutions somehow to get a solution for the whole. All right, what are the properties that we need to achieve in order for this methodology to work? Number 1, whole to part. That is, if we partition this graph into different pieces. Does an optimal solution, or any solution, for the whole graph induce solutions on the parts? So let's, for example, break it up this way. So let's say I just break it up in a simple way, like that. Oh, that color is not so good. Okay, so we partitioned it into two parts. Ordinarily, we partitioned it to many more. Is it the case that a solution for the whole graph induces solutions on the parts? All right, who thinks yes? Okay, can you make an argument why it is? I mean, it's simple, right? Right, right. If every pair of terminals is disconnected in the old graph, it's disconnected in the new graph. Exactly so. All right, so whole to part is not a problem. Now, a part to whole depends on exactly what decomposition we use. Remember, we looked at decompositions in which the parts overlapped or were spaced apart differently. But I want to argue that no decomposition of this form is going to work for this problem at all. If I divide it into pieces, let's say I divide it into the pieces shown here. A solution to each of these problems independently, if you take the union of those solutions, you're not going to get a solution to the original instance. So why is that? So suppose I manage to solve this part. What's the solution to this part, by the way? Sorry? Empty set. This one, all right, I disconnect these three terminals. Now I union the two together. Well, the union of the solutions does nothing to separate this terminal from the ones in the other parts, the other part, right? So the union of solutions to the parts in this problem is not a solution to the whole. Parts to whole does not work at all. So we need a better approach. We need to augment the solution obtained for the parts to get a solution for the whole. Any suggestions? There's a simple approach you might try, right? Very simple approach, right? What do we need to add if we... Who said? Yeah? Perfect. If we add the edges crossing the partition to the solutions for the individual parts, we'll have separated all the terminals. If two terminals lie in the same part, they're separated within... Consider a path between two terminals. If the path stays within a part, it's separated because we're including the edges for the solution for that part. If the path crosses, we're breaking that path because we're including in the solution all edges between the parts. Good. So it's in the case of yesterday's methodology, and there's a very good reason why we didn't. Okay. So why is it? What's the challenge here? Remembering that we want to achieve an approximation scheme. We want, for any epsilon, we want the algorithm to achieve a solution whose cost is at most 1 plus epsilon times optimal. So what's wrong with your solution? I mean, it's an excellent solution, and it's in some sense what we're going to have to end up doing. But what's wrong with it?
We have to find partitions so that the edges crossing are at low cost.
Exactly. You're adding those edges across. So the idea is that you'd add these. Let's see, I've got all these colors, but so you'd add, say, these edges. You're adding those to the solution. You're increasing the cost of the solution. At the same time, you don't want to increase it to where it's far more than opt. So we have to make sure that the edges crossing that partition have low cost. Low cost in what sense? Low cost meaning their weight should be at most epsilon times the weight of the optimal solution. Good? All right. Now, what technique did we use? How did in yesterday's lecture, what did we do to make sure that some set of edges or vertices had low weight? What was the technique we used?
We use k different decompositions.
K different decompositions.
Such that these overhead edges are exclusive. I mean, compared to opt are exclusive in all those k decompositions.
That's right. That's right. So you have each partition, each decomposition specifies a set of, let's say, edges, and they're the ones that are supposed to be cheap, and they're disjoint across the different decompositions. So the sum of the weights of those edges is at most, in the case of yesterday's methodology, the sum of the weights is at most opt, because we were only including edges in opt. Okay, we were including in that analysis, and so the sum was opt. So to make sure that we only had a total weight of epsilon opt for these edges that we didn't like, we chose k to be 1 over epsilon or so, and then at least one of those decompositions had the right property by averaging. If they were all too heavy, then the sum would be too big. All right, so what do you think? Should we try that approach here? What would it mean to apply that approach here? So let me give you a decomposition. Let's see. All right, so we're going to use these breadth first search levels again. Okay, so we're just going to do the simplest thing. Use some consecutive sequence of k levels. Do another sequence of k levels. And so on. Okay? By shifting this thing, by choosing different starting points, we get the edges separating become different. So this is maybe level Q, edges, level Q plus K, edges, and so on. So by taking k shifts of this decomposition scheme, this decomposition pattern, we hit each edge of the graph at most once. Some edges we don't hit at all. Okay, so we have k different decompositions by shifting it. So one of those decompositions, what can we say about one of those decompositions? No. That's the right idea. So here's the problem. Okay. We're not talking about opt here. We're talking about all the edges across here. All the edges across here. So what can you say? And try again. You had the right idea.
You can only say total weight, right?
Yeah, go on, elaborate.
So if all edges are included at most one, we can only say total weight divided by 3.
That's right. That's right. So, so how's this go? So you say, sum over I, weight of edges at level congruent to I. That's less than or equal to weight of all of G, not opt, the graph itself. Now, admittedly, some of the edges of G won't be counted at all there, but we can't really make use of that fact. It may be that most of the weight lies in these cuts. So we can say there exists, we'll say I hat, such that weight of edges at levels congruent to I hat is less than or equal to 1 over k times the whole weight of G. Now, is that going to be enough? So remembering, the set of edges crossing the partition is the set of edges that we're going to add to the solutions. So it's going to increase the weight of the solution. And we want the weight of the increase to be epsilon times opt. All right, well, it's not immediately clear that we can choose k so that the 1 over k times weight of G is at most epsilon times opt. You got two choices. You can have k, so the graph itself might have a total weight that's much, much bigger than opt. So what do you do in that case? There are two possibilities. One is you set k to be very, very big to compensate. That's not so good. Why? How does k factor in the running time? Well, it's more that that's right. You have to choose k so that 1 over k times weight of G is at most epsilon times opt. How does the running time depend on k? It's exponential in k. So that's not going to be a very good algorithm if the weight of G is much bigger than the weight of opt. What's the alternative then? I mean, is there an alternative? This term, how can we make this smaller? How can we make this term smaller? One is to make k very big. We see that that's not a good solution because that leads to exponential running times. There's only one possibility then. We have to change the weight of G. So, let's see. We have to transform, say, G input to some graph G. And what we want to be true of this transformation, what do we want to be true? What's the main thing we want? What's the first thing that comes to mind? Why are we doing this transformation at all? Yeah, one of the two directions.
So, because we're working with G, right? So, we will find a solution in G and transfer it back to this equation, right? So, every multi-terminal cut in G should be a
Good. We'll say a feasible solution in G must be feasible solution in G input. Okay, so a multi-terminal cut in G, since that's what we're going to return a multi-terminal cut in G, and it had better be a multi-terminal cut in G input, because that's the graph that we originally wanted the solution to. All right, so that's property one. What's another property that we'll need for this? Why? Good. That's excellent. Why is that? Because, yeah, so why do we need that? That's exactly true, but why do we need that? I mean, it wouldn't do any good if we derived this graph from G input, we derived this graph G, we said, oh, now we can find a nearly optimal solution in G. But the nearly optimal solution in G is vastly more expensive than the solution in G input. So then we go and return the nearly optimal or even the optimal solution in G in, say, hey, I did a great job. Here's the optimal solution in G. Well, that's no good. I wanted a solution whose cost was comparable to the optimal solution in G input, the original graph. So we need that, I'll write it this way, the weight of an optimal solution in G is at most, let's say 1 plus epsilon times the weight of an optimal solution in the original graph. All right? So whatever this operation is, it had better not increase the weight of this optimal solution by very much. We're going to allow a little bit of slack. All right, there's one more property which has to do with why we're actually considering this kind of modification in the first place. Why would we bother? Why are we transforming G input into G anyway? Does anyone remember?
So weight of G should not be too larger than weight of opting.
Right. Weight of G is at most some constant, let's say, times the optimum in the original graph. So we're going to thin this graph down to something that has many fewer edges. Now, how are we going to transform G input? What process do we do to carry that out? And in graph theory, there are there's basically two operations that we like to do on graphs to get rid of edges. So you see the idea? To get the third property, we're going to have to eject some edges, throw them out of the graph. The heavy edges we don't want in there. Let's say you had a really heavy edge. Let's say it was infinite. Well, throwing it out seems like a good idea, right? That'll help us to achieve this. What about this? How will it affect this? Well, if it was a really heavy edge, it's not likely to be used in opt anyway. But what do we do? What does it mean to throw out this heavy edge? Let's say you have a really heavy edge, nearly infinite weight, and you're trying to solve the multi-terminal cut. What is it? How do we throw it out? What are the two ways you can remove edges from a graph? Deletion, contraction. What should we use here? Let's say we delete some edge. We're expecting that we're expecting this transformation is going to slightly increase the weight of opt. What does deletion do for this problem? Does deletion make it easier or harder to get a multi-terminal cut? Makes it easier. So actually, if you delete a bunch of edges, hey, great. The optimum solution is not going to go up by much. In fact, it may go down way down. So is that good? Is that good? How does that relate to condition 1? One would not be necessarily true. Right. So if you start with a graph and you delete some edges from it, a feasible solution in the new graph, that is a multi-terminal cut, would not necessarily be a multi-terminal cut in the original graph. All right? We ruled out deletion. What do we got left? Contraction. So if we contract edges of very high weight, what could that do? Right? Certainly, if we contract edges, if we unify vertices, property 1 will be true. Right? A feasible solution, if the solution, if a solution manages, if a set of edges manages to disconnect the terminals in G, well, certainly it's going to disconnect them in G input. Things are sort of closer in G than they are in G input. So 1 will be true. 2, well, we have to figure it out. We have to figure out how we can approximately preserve the opt solution and still throw out enough weight that 3 is true. All right. So here we have to consider not just so there's an algorithmic question. There might even be a mathematical question. Does such a thing exist? Is there any set of edges is it true that for any graph G input, there's a set of edges that you can contract so as to achieve this property? Maybe it doesn't even exist. Can someone give me an argument as to why it exists? Does there exist a set of edges to contract to go from G input to G so that all those properties hold? You know, if there's no guarantee that even such a set of edges even exists, well, this methodology is doomed. All right, so I'll draw a graph again. And let's say we had some terminals. I keep drawing this graph. The multi-terminal cut for in a planar graph when the terminals are on the boundary of a single face, you can actually solve in polynomial time. Polynomial? No, not quite. There's an easier solution to that. But anyway, we're going to ignore that. Maybe there's a polynomial time solution. Maybe not. Think about that. Anyway, so does such a thing exist? So we're looking for a set of edges to contract. So let's say, does anyone have an idea? I'll give you a hint. There is a very simple existence proof that helps us not at all computationally. I can demonstrate to you that there is such a graph G. But that demonstration does not help us at all in the algorithm. Excuse me? Suppose you knew opt.
Contract edges which have size greater than the maximum edge.
No. But suppose you knew opt. That's a great starting point.
We contract the non-opt edges.
Yeah. Contract the non-opt edges. Right. So let's say opt look like what's a good opt? Okay. We have to disconnect this from everything. Are we done? So I'm going to draw in the dual. You can still get around here. I'll do that. And, yeah. Okay. All right, so we've drawn, it's easy to see, in this problem it's easier to see it in the dual. I love the planar dual. So this is a partition into parts where each part contains one terminal. So what do? We contract everything, we contract all the edges within each part. These are the edges that are not in opt. Okay, what do we get? All right, we unify, coalesce these nodes, all these nodes. You get one big node there. Do the same thing here. All right. So we've done all these contractions, and now what's true? Is it true that a feasible solution in that graph is a feasible solution in the original graph? Yeah, that's just by virtue of their having done contractions. How's the weight of this graph compared to the weight of opt of the original graph? It's the same. So part 3 is trivially true, and part 2, well, the weight of the solution hasn't gone up at all. The same solution exists for you to find. So that shows that this is not a completely ridiculous goal. Okay, there is such a solution. All right, so now so this is the methodology we're going to use. How do we achieve the approximation? Back here, we now have a value we can set for k. So if we set k to be C over epsilon.
So in the earlier picture, the red lines are the non-terminal edges. Is it like that?
Sorry?
The red lines, what are the red lines? Are they non?
The red lines, well, I use red for two. The red lines are the edges of opt. The optimal multi-terminal cut.
So they need not all be non-terminal edges. Not necessarily.
Well, there's no such thing as I don't know what you mean by non-terminal edges.
No, none of them touch the non-terminal.
They don't have to touch they don't have to, I don't care what they touch. So you see what we're doing? We're setting k to be C over epsilon. What does that do? So the weight of G, so I'll write out the equations. Okay, so first the algorithm. So somehow we compute this G from G input. Is this lectern in the way? It's, I don't know. Sorry. All right. Set k to be C over epsilon. For I equals 0, 1, up to k minus 1. Compute the weight of the set of edges at level congruent to I. And that I hat equal whichever one achieves the smallest weight. So that shows, so now we've got a set of edges with small weight, and it partitions things up. And each of the parts, what's the property that each part has that enables us to compute things on such parts? Each part consists of only k levels of breadth first search, and therefore the hop distance is low. Well, so the branch width is low. So we can solve it optimally. And finally, we have to find a solution for the graph G. And how did we do that? So we found optimal solutions for the parts. What did we have to do to their union in order to get it to be a solution for the whole? Can't hear. Did someone say? Add the edges? Yeah. All right. I just erased the crucial thing, but what's the cost, what's the weight of the resulting solution? Well, there are two parts. Is the weight of the solution, of the sum of the weights of the solutions to the different parts. Plus the weight of removed edges. Okay. Now, the sum of the weights of the solutions for the different parts, well, by the whole to part property, we know that there's a solution in each part such that the sum of those weights of solutions is at most opt for G. So this part is at most weight of opt of G. This part is at most 1 over k times the weight of the whole graph G. All right, next step. What do we know about weight of opt of G? Oh yeah, there's a property. So that's less than or equal to 1 plus epsilon weight of opt of G input. And what do we know about this 1 plus k weight of G? Sorry?
G by k times weight of G.
Epsilon by 1 over epsilon.
What is it?
Epsilon by 1 over epsilon.
1 over k. So we set k to be c over epsilon. So it's epsilon over C. Now, we have a bound on the weight of G from this property. C times, this should be weight, of opt of G. G input. Thank you. Okay. So putting that together, it's 1 plus epsilon weight of opt of G input plus epsilon weight of opt of G input. So weight of two epsilon, 1 plus 2 epsilon weight opt. So this is success. We wanted to get a 1 plus epsilon approximation. We got a 1 plus 2 epsilon. That's okay. The dependence on epsilon is such that we can just, if we wanted a 10%, if we wanted a 10% error, we just plug in epsilon equals 5%. And this works out.
Basically, you take these rectangles, and each of them you try to find the there's some edges crossing the rectangles. Those are what you call as removed edges. Is it like that?
Those are what I call,
Is that what you're terming as removed edges or something else? Removed edges.
what is the word?
Removed edges.
Remove these removed edges, right. That's right.
The crossing ones are what you're calling.
That's exactly it.
Actually, earlier we proved that there exists an I-cap for which the sum of the edges is upper bounded by the weight of the graph, 1 by k times the weight of the graph.
Yes.
So what that, how it mapped to the cycle.
This is what I'm using here. The weight of the removed edges is at most 1 over k times the weight of G.
Okay, there exists one I-cap, but how sure are you that those crossed ones are same as that I-cap?
Good. That's a good question. Yes? Take the smallest. Yeah. We have k different decompositions. They're all disjoint with respect to the edges removed. So just one of them, you just look at them. You can add up the weight. And the smallest one is guaranteed to be at most 1 over k.
So basically you're looking at the edges which are going from one rectangle to the other.
Yes?
So, but this I-cap can be anywhere in between also. It need not be at the boundary. Right?
No, this I-cap is just you have these different partitions, right? Okay, so one partition looks like this. Another partition looks like that, right? And so on. I'll do one more. Okay? And the edges that you have to separate, in this case, it's these edges. In this case, it's these edges. These. Okay, so they're all disjoint. So you just, once you find those, once you consider each partition, then you look at which edges would be removed if you use that partition.
One of the decompositions that I-cap will be there.
Sorry?
In one of the decompositions that I-cap will be the boundary. So that is
Okay, I didn't quite hear.
these are different decompositions.
Different decompositions.
One of the decompositions I-cap will be the boundary.
I don't know. It's the boundary of the of the decompositions. That's right. I think that's what you said. All right. So now I'm going to switch gears. This is the new formulation. I haven't told you how to how to find which edges to contract. And I'm not going to tell you in these lectures. For the multi-terminal cut problem, I have a solution. We published it very recently. It's very complicated. I think there's going to be a good, simpler solution, simpler than what I have, but I can't be sure. There is a solution, but it's hard. So what I'm going to do is switch to another problem where it's a little bit easier to do that. Yes? Is it always easy to find? It's an excellent question. No. So what do we know about these blocks, these parts? They have low branch width. So the question is, are there problems for which maybe it's too hard to find it even if the graph has small branch width? And that's true. There's one interesting thing that you can do. Suppose in fact it's NP hard, even in a bounded branch width graph, even in a graph of branch width 3 or 4. Okay, it's still hard. Can you see a slight weakening or slight variant of this framework that will possibly enable you to make progress anyway? Find an approximate solution. Exactly right. Yeah. So there have been papers along those lines as well that use the same framework, but when it gets down to the bounded branch width problem, then you use an approximation even there. So it's a good question. All right. So I'm gonna switch to the. I want to show some things on the computer now. All right. Can we turn out the lights? Okay, so here's the motivation. So the problem we're going to look at is this out of focus or is that me? Can we focus? Can they focus it a little bit? So let me explain where we're going now. The steps in our methodology now are: we first do some contractions, and that gets the graph to have low weight. Then we find these partitions, and based on each partition, we do some deletions. That is, we choose the best partition, and we delete the edges. Is that right? Now, we know that contraction and deletion are dual operations. So this methodology can be flipped into the dual. So in the first step, we delete edges, and in the second step, we contract edges. So we're going to use that framework in the next. This is worse. Are they? They're fixing it? Should I wait? Or do I have to change the resolution? It worked. The same resolution worked yesterday. Are they really fixing it? There's no one in there. Someone's reappearing. That looks a little better, but All right, well, I guess we'll just go ahead. Okay, that's a little better, maybe. All right, so the first step is we're going to delete edges. And the idea is that we don't want to increase the weight of opt by too much. We want to increase it by most of 1 plus epsilon factor. So let's say we take out those edges. And the goal is to ensure that the value of opt for the resulting graph is at most a constant times, that the weight of the resulting graph is at most a constant times opt in the original graph. Okay, so now we contract some edges. All right, so here's what we did first. The first step, we delete. So now we have a solution. We have a low branch width graph. We apply some branch width algorithm, some dynamic programming algorithm, to find, let's say, the optimal or the near optimal solution in that low branch width graph. But now we still need an optimal solution in the original graph. So we have to incorporate somehow the edges that were contracted to lift the solution from being a feasible solution for the contracted graph to a solution for the uncontracted graph. So that's this fourth step. Okay, and here's the dual framework, the framework we used to address multi-terminal cut. Contract some edges and then delete edges. And otherwise it's pretty much the same, although the detail is different. And we choose P big enough so that the total increase due to lifting is at most epsilon times opt. Okay, this is just illustrating the idea. Here's this breadth first search. These are the edges at level 0. These are the edges at level 1, level 2, and so on. We color these. We assign colors mod P. And we choose one of those color classes, whichever one is the least costly. And we define a partition for which those edges, those least costly edges, are the ones crossing the parts of the partition. Okay. All right. So now we're going to look at the traveling salesman problem. Who knows what the traveling salesman problem is? Okay. So for those who don't, traveling salesman in a graph, you have a salesman who has to go around delivering or selling, has to visit a whole bunch of different locations. And the order matters. If you go from, the salesman wants to choose the order of locations to visit so as to minimize the total tour length. So let's say you want to do this in a graph. So you have a graph with edge weights. You want to visit all the vertices of the graph. Make a tour and come back to the beginning while minimizing the total tour length. So you're allowed to travel through edges more than once. You just have to visit each vertex at least once. So our goal here is to find a set of edges to delete so that we have those properties. So that you can't, the invisible properties now. What are the properties we need? We need the total weight to be not too big. We need to approximately preserve the tour length. And in order to ensure that a feasible solution for the resulting graph is feasible for the original graph, we're going to carry out some deletions. So deletions are the right thing to do for the tour. If you have a tour in a graph, let's say you start with G input, you delete some edges, now you find a tour in the resulting graph. Well, that tour in the resulting graph after deletions is certainly still a tour in the original graph. It didn't use any of the deleted edges, but okay. So now, so what our main focus is on how to preserve up to some 1 plus epsilon factor, how to preserve the length of the optimal tour. All right. So any ideas about that?
Stuart, ensure there is a Hamiltonian cycle.
Well, now let's distinguish between a Hamiltonian cycle is a graph object. A Hamiltonian cycle is a cycle that visits each vertex exactly once. We're not interested for this problem in Hamiltonian cycles because that's too hard. We can't do that.
But this must be Euler tour, right? Because
No, it's neither of those.
because Stirling Salesman problem is minimum cost Hamiltonian cycle.
No, it's not. So I can explain where that misconception comes from, but let's not do it now. So the goal is to traverse the graph, visiting each vertex, and minimize the total tour length. So this is distinct from Hamiltonian path, but I understand the misconception. We can talk about it afterwards. Okay. So a tour. Let's say you know the order of the locations to visit. You know which vertices. You know the vertices to visit. You know the order in which to visit the vertices. On your way from, say, vertex 1 to vertex 2, what are you going to do? Let's say you're supposed to visit vertex 1 and then visit vertex 2. How are you going to get there? You're going to take a shortest path. So once the order is selected, to go between vertices, you're just taking shortest paths. Now, how could we do damage by removing edges from this graph? How could we cause that tour to be a poor one? Sorry? What about the shortest path? Increase the shortest path length. Excellent. So what if, on the other hand, what if we don't increase the shortest path length by very much? Will that work? Right. So if in removing edges from G input to form G, no shortest path length is increased by much, then we will succeed. Well, at least that aspect will be okay. So for every pair of nodes, we want to approximately preserve the distance between those nodes. Okay. So that's going to be our goal. So let's see how that works. So, for example, suppose the tour looks like this. We might delete these edges, but maybe we can reroute the tour along here. And maybe the goal is that the path length, the shortest path length, won't increase by much. Okay. In particular, between each pair of nodes visiting, we replace an edge that maybe is omitted by a 1 plus epsilon approximate shortest path. That is, a path whose length is at most 1 plus epsilon times the length in the original graph. Then we will have increased the total tour length by at most a factor of 1 plus epsilon. All right. So our goal is to select a subset of edges that approximately preserves vertex to vertex distances. All right. Now, how would we do this? Just to start us off with some intuition. Suppose all you want to do, you have a graph, presumably it's connected, otherwise you can't visit all the vertices in one tour. Suppose all you want to do is make sure, you want to delete edges so as to make sure that the path length between any pair of vertices remains finite. What's necessary just to achieve finite path length between any pair of vertices? Spanning tree. Now, if we want a minimum length solution, we want the total weight of the resulting graph G to be small weight, right? So what's the best choice of spanning tree we could take? The minimum weight spanning tree. So that's going to be a good starting point. So the weight of the minimum spanning tree will define by M of MST. Or the minimum weight spanning tree will define by MST. So what we want is to choose the minimum spanning tree. That's enough just to achieve connectivity, just to achieve finite distance between any pair of vertices. And then we want to add some more edges. We don't want to add edges of too much weight. We want the total weight to be not too much more than the minimum spanning tree length. Okay? In particular, we could achieve 2 over epsilon times the weight of the minimum spanning tree. So that much additional weight will suffice to achieve a 1 plus epsilon approximation in tour length. All right. So now I'm going to describe the algorithm.
I thought we are deleting edges. What are these additional edges?
I didn't get that, but I messed up the... Sorry?
We started with the goal of removing some edges.
We're removing some edges.
The additional edges mean same thing.
I see. Yeah, I didn't explain it well. So we start with G input, and we want to delete edges so that we get a graph G whose total weight is not too big. Okay? How am I going to select G? Well, I know that G had better include the minimum spanning tree. Okay, what other edges need to go into G? So now I'm going to give you an algorithm to decide which other edges to go into G. The edges that we don't put in G, we're going to delete those. Okay? All right, so here's this set of edges. Here's this graph that we start with. So first let's find the spanning tree, the minimum spanning tree. So here's the original graph, and now let's say these are the spanning tree edges. Now conceptually, what we're going to want is we want to think about shortest paths that don't pass through the spanning tree. So to make that more concrete, we'll say we cut along the edges of the spanning tree and we duplicate them. So just imagine this is a graph embedded on a surface. Just take your scissors out and cut the surface. Right? So you cut along these edges, and this is what you get. And now you pull it apart a little bit. You slightly widen it. Okay? And here's what you get. So what have we gotten? We've gotten this new face. Okay? And what we did, we duplicated edges and vertices as necessary. That's the graph operation of cutting involves duplicating edges and vertices.
What did we cut along?
The minimum spanning tree. So this is the minimum spanning tree. We cut along those edges.
First one, there are 2 graphs here. One on the left and one on the right.
So here's the input graph. Here we find the minimum spanning tree for that input graph. And now we cut along it in the original graph. Is that a little clear?
First one is just, you slice it out and you got a second.
Sorry?
You slice it out and you got a second. More than that is nothing.
You're talking too fast for me.
The left one and the right one, both are the same, but only
Oh yeah, this is just a picture. There's no difference between these two. This is just trying to give you a physical intuition. Good? All right. So okay. So next, what do we do? Yeah, so now this is just for intuition. This isn't actually involved anything. Remember we can consider any face to be the infinite face. So I'm going to take this thing that we got by ripping open the tree, cutting into the tree, and consider that the infinite face. So this is just for presentation. So this part. So imagine this embedded on a sphere, and make this part bigger and bigger until it looks almost like the infinite face. All right. Now, we're going to consider the non-tree edges, the edges not in the minimum spanning tree, in a certain order. I'll talk about the order later. And now we're going to decide whether we want to include them. These are additional edges that have to go into G in order to achieve a 1 plus epsilon approximation in distance. Okay? And now we consider them in this order, this as yet unspecified order, and we consider, do we need to add this edge or not? So here, let's consider this edge. Do we need? Well, one condition for under which we don't need to include this edge is if the corresponding bit of boundary is short enough. If the length of this boundary, so we're considering this edge. If this edge is not much shorter than the length of the boundary next to it, then we might as well leave the edge out. The path, it's already well represented by the boundary. Is that clear? Okay. So there's that edge there's an edge we consider, and we look at the corresponding boundary there, and we compare. Now, what does it mean? What's the rule? We say if the weight of the edge is even when we multiply by 1 plus epsilon, it's still less than the weight of the boundary subpath. Then we really do have to include this. Then we have to include the red edge in G. And there we did it. So we added that edge and we cut off that boundary. So you can think of removing bits of the boundary. Okay. Next we consider this edge. Okay. And how do we decide whether to keep that edge? We compare its length to the length of the corresponding boundary. If even multiplying the length of this by 1 plus epsilon, it's still shorter than this, then we better include it. Maybe it's not. In that case, we just throw it away. We go on to the next edge. So let's say it looks like this. If this edge is shorter than the boundary, even after multiplying by 1 plus epsilon, we put it in and we throw away that part of the graph. All right, now for the analysis. We only included an edge and cut along it if its length was so small compared to the boundary length that even if we multiply the length by 1 plus epsilon, the boundary length is still larger. So by replacing the bit of boundary, the boundary subpath, with that edge, we're actually reducing the length of the boundary. Okay? We're going from before we cut along it, the boundary length was at least 1 plus epsilon times the length of the edge. And after you do it, it's exactly the length of the edge. So the difference, the reduction in the boundary length due to that step, is at least epsilon times the length of the edge. Every time we include an edge in G, we reduce the boundary length by at least epsilon times the length of G. Is that okay? So how much weight do we add to G? What's the total length that we add to G? Every time we add an edge to G, we're reducing the boundary length by at least epsilon times the length of that edge. So how much can the boundary length go down? It's the weight of the spanning tree. Almost. What? Right. So the total, you're both right. So the bound on the decrease is epsilon inverse times the total change in the boundary length from the beginning to the end of the algorithm. Okay? Epsilon times the weight of G, times the added weight, the weight of edges added to G, is at most the decrease in the boundary length. Now what's the initial boundary length? Before we carry out this iteration, even the first iteration, what's the original boundary length? Twice the minimum spanning tree. Right. Why is it twice? Exactly. So the initial length is twice the boundary. Finally, at the end, it's at least 0. So the total decrease is at most 2 times the minimum spanning tree length. So multiplying that by epsilon inverse gives you the weight of the minimum spanning tree. Sorry, 2 times epsilon inverse times the weight of the minimum spanning tree gives you a bound on the additional weight added to G. Now, all we wanted, remember, was that there be some constant such that the weight of G is at most a constant times the weight of opt. So have we achieved that? In particular, how does the weight of the minimums, we were trying to address the traveling salesman problem. Find the minimum tour length. How does the minimum tour length relate to the minimum spanning tree cost?
Two times that, 2 times.
Yeah, but in fact, the other way around, the minimum spanning tree length is at most the tour length. Right? You take any tour, that includes at least enough edges to build a minimum spanning tree, to build a spanning tree out of. It's probably not the minimum. So what this shows is that you can achieve a graph G by deletions that has the properties we need. Okay? We got it by deletions, so it has property 1. Property 2, which we can't see anymore, is that its weight, the weight of the optimal solution, the optimal tour length, is preserved up to a 1 plus epsilon factor. That we achieve because there's a because we preserve distances up to a 1 plus epsilon factor. And finally, the weight of the solution, the weight of G, it's at most, it's roughly 2 times epsilon inverse, at most 2 times epsilon inverse times the value of the optimal solution in the original graph. Okay, so we get this theorem. There exists a subgraph of cost 2 times epsilon inverse plus 1 times the minimum spanning tree cost, such that distances are preserved approximately. This is what I mean by distance preserved. For every pair of vertices in the graph, the u to v distance in the subgraph G is at most 1 plus epsilon times the u to v distance in the original graph, which I should have written as G input. I wrote as G. So plugging this into the framework, yeah. Yeah, good question. Let's come back to that in a moment. Because this is only true for planar graphs. Or rather, it's not true for general graphs. So using this in the framework, we get this property. That there's in fact a linear time algorithm for this spanning tree, for this traveling salesman problem. So can we have the lights on again? Okay. what does this have to do with planarity? Well, I didn't specify the algorithm entirely, right? What did I leave out? Does anyone remember? The order. Okay. This idea of, so what does it have to do with planarity? Well, we had this measure of progress, which was the length of the boundary. Okay, the boundary of the outer face, the infinite face. So that you can't really talk about the outer face or anything of an arbitrary graph. Okay, so what property do we need of the order? Okay, so here's the graph initially. So I'm going to go back to thinking in terms of the minimum spanning tree. So let's say this is the minimum spanning tree. And we want to consider adding edges. So all this business about cutting up, that's mostly for implementation and for you need to do that for the implementation, and you need to do that maybe for intuition. But we can go back to thinking about the graph before we cut it up, and just make sure that we consider shortest paths that don't pass through the tree. That's essentially what it means to cut along that thing. So now we consider an edge, and we want to decide whether to add it or not. Okay? So we consider, say, this edge. Okay? If we decide to add it, we're basically expanding this. So we disregard all this stuff. Now maybe we consider this edge. If we decide to add it, let's say we decide to add it, we throw that all away. And in this way, our intention is that every edge is either included or is approximated. Meaning if we don't include it, there's some path in the set of edges we've already put in G, which a subpath that has about the same length. All right. Now, if I'm not careful about which order to put things, to consider the edges, what could go wrong? All right. Let's say the next thing I do is consider this edge, for example. Why might that be a bad idea? Okay, so there are no vertices inside the face because this is a spanning tree.
So there is an edge that particles this face.
Exactly. There might be more edges in there. If you choose the order without much care, let's say I decide, oh, this is a good edge to choose, then I basically wipe this whole thing out. Good. Very good insight. So now, how should I choose it? Any ideas? Not from you. Got a ringer in the audience. Any ideas from the students? Can I can't hear.
Can you choose the vertices of the minimum spanning tree along the minimum spanning tree such that the faces they are clearly consecutive, like which comes immediately after, and the non-edges. Suppose you is a non-edge, then we try to order them so that in the minimum spanning tree they come.
Good. So I see. Yes. So what you would say is travel along the minimum spanning tree. It's called an Euler tour. And now you want to choose edges that minimize the gap. Yes. Excellent idea. That would work very well. I'm gonna push for a slightly different formulation that will, and because it's easy to implement in linear time. But that's a great solution.
So what was told was converting oscillator to cycle. Is that
So the idea was to consider edges that don't, when you have two edges to consider and you had to choose between them, choose the one that has a smaller range of vertices. If you number the vertices along the minimum spanning tree, now you have to be careful because a vertex occurs multiple times in the minimum spanning tree. So you have to consider it according to its multiplicity. Okay, so that's a good solution, but I want to move to another way of thinking about it because it connects back better with the other stuff I talked about. Okay. The interdigitating tree. That's right. So let's look at all the edges that we might have in this graph. So let's say we have an edge like this, edge like this. All right. Probably enough edges. I don't know. All right. So let's draw the interdigitating tree. Oops. Okay. And now, there's a natural root to use, which is the infinite face, right? Now, you know that the choice of infinite face is oftentimes arbitrary. So, but I've drawn it this way, so we can consider it this is the root. And now all you do is consider the edges leaf to root. And that will achieve that's another way of achieving the same thing. Okay, so which edges are you going to, right, for example, first you have to include one of the leaf edges. So this edge, for example, you might consider, or this edge. And that guarantees that when you consider an edge, you will have already considered all the edges that are enclosed by the cycle, the fundamental cycle it forms. Right? So by the time we consider, say, this edge, this rule of going leaf to root in the interdigitating tree will ensure that we've already considered all the edges enclosed by this fundamental cycle. Okay. So another use of the interdigitating tree. So the history of this algorithm, just to mention briefly, and then we'll wrap up. There existed an algorithm that achieved this bound for finding this subgraph that preserved distances. It was a slightly different algorithm than what I presented. And the people who came up with it weren't that interested in the running time. They just wanted to show existence, and it was clear it was polynomial. And I was submitting the paper on traveling salesman. I submitted to some conference, and it was badly written because I had just figured it out, and it was not quite worked out. And I didn't have this algorithm, so the algorithm wasn't really linear time because for one thing, finding this subgraph G I didn't know how to do that fast. I knew I could do it in polynomial time, but I didn't know how to do it fast. And then I went to bed, and then I realized, oh, of course, it's the interdigitating tree, or you can consider these edges in order, and the original algorithm considered the edge and said, include this edge only if every shortest path between its endpoints in the existing graph, in the graph you've chosen so far, is too long. But I realized that for the analysis, all you need is that boundary length. So it's a slight change to the algorithm, but it makes it easy to run in linear time. Okay, so we're going to stop for now, I guess. And when we resume, we'll talk about how you might extend this this framework to deal with maybe a more natural problem. Here we considered a traveling salesman tour that visited all the vertices. But in my favorite setting for planar graphs, which is maps, city maps, you very rare, the city map has a vertex for each intersection in the whole city, right? You very rarely have to visit every intersection. More often, you'll visit a subset of the vertices. So we'll see how this framework can extend to that problem when we return.